Now I am going to talk about the thermodynamics. Thermodynamics is the study of relations between heat, work, temperature and energy. There are four important laws of thermodynamics. They are zeroth law of thermodynamics, first law of thermodynamics, second law of thermodynamics and third law of thermodynamics. Zeroth law of thermodynamics. The zeroth law of thermodynamics states that if two bodies are individually in equilibrium with a separate third body, then the first two bodies are also in thermal equilibrium with each other. This means that if system A is in thermal equilibrium with system C and system B is also in equilibrium with system C, then system A and B are also in thermal equilibrium. An example demonstrating the zeroth law, this given diagram represents the zeroth law of thermodynamics. Consider two cups A and B with boiling water. When a thermometer is placed in cup A, it gets warmed up by the water until it reaches 100 degrees Celsius. When it reaches 100 degrees Celsius, thermometer is in equilibrium with cup A. When we move the thermometer to cup B to read the temperature, it continues to read 100 degrees Celsius. The thermometer is also in equilibrium with cup B. By keeping in mind the zeroth law of thermodynamics, we can conclude that cup A and cup B are with each other. First law of thermodynamics. First law of thermodynamics, also known as the law of conservation of energy. First law states that energy can neither be created nor destroyed, but it can be changed from one form to another. First law of thermodynamics examples are plant convert the radiant energy of sunlight to chemical energy through photosynthesis. We eat plants and convert the chemical energy into kinetic energy while we swim, walk, breathe and scroll through this page. Switching on light may seem to produce energy, but it is electrical energy that is converted. According to this law, some heat given to the system is used to change the internal energy while the rest is used in doing work by this system. It can be represented mathematically as del Q equal to del U plus W, where del Q is the heat given or lost, del U is the change in internal energy, W is the work done. We can also represent the above equation as follows. Del U equal to del Q minus W. The given diagram represents the first law of thermodynamics. Here the state 1, the water molecules are compressed. When the water molecules are compressed, the heat and work are released to the state 2. Second law of thermodynamics. Second law of thermodynamics states that the entropy in an isolated system always increases. Any isolated system spontaneously evolves towards thermal equilibrium, the state of maximum entropy of the system. Second law of thermodynamics mathematically represented as del S universe greater than 0, where del S universe is the change in the entropy of the universe. Entropy is a measure of the randomness of the system, or it is the measure of energy or choice within an isolated system. It can be considered as the quantitative index that describes the quality of energy. Meanwhile, there are few factors that cause an increase in entropy of the closed system. Firstly, in an isolated closed system, while the mass remains constant, there is an exchange of heat with the surroundings. This change in the heat content creates a disturbance in the system, thereby increasing the entropy of the system. Secondly, internal changes may occur in the movement of the molecules of the system. This leads to disturbances which further causes irreversibilities inside the system, resulting in the increment of its entropy. There are two statements on the second law of thermodynamics, which are Kelvin-Planck statement and Clausius statement. Kelvin-Planck statement. It is impossible for a heat engine to produce a network in a complete cycle if it changes heat only with bodies at a single fixed temperature. Example, if Q equal to 0, the heat engine produces work in a complete cycle by exchanging heat with only one reservoir, thus violating the Kelvin-Planck statement. Classius statement. It is impossible to design a device which works on a cycle and produce no other effect other than heat transfer from cold body to hot body. That is, heat transfer can only occur spontaneously in the direction of temperature decrease. For example, we cannot construct a refrigerator that operates without any work input. Example, a refrigerator with cope equal to infinity, which is impossible. The given diagram represents the Clausius statement. For example, there is one hot reservoir and cold reservoir. There is no heat transform from cold reservoir to hot reservoir. Next, third law of thermodynamics. The third law of thermodynamics states that the entropy of a perfect crystal at a temperature of 0 Kelvin, absolute 0, is equal to 0. At a temperature of 0 Kelvin, the following phenomena can be observed in a closed system. The system does not contain any heat. All the atoms and molecules in the system are at their lowest energy points. Therefore, a system at absolute zero has only one accessible microstate, its ground state. As per the third law of thermodynamics, the entropy of such a system is exactly zero. The given diagram represents the third law of thermodynamics. Mathematical explanation of the third law. As per statistical mechanics, the entropy of a system can be expressed via the following equation: S minus S naught equal to KB ln ohm, where S is the entropy of the system, S naught is the initial entropy, KB denotes the Boltzmann constant, ohm refers to the total number of microstates that are consistent with the system's macroscopic configuration. Now, for a perfect crystal that has exactly one unique ground state, ohm equal to 1. Therefore, the equation can be rewritten as follows: S minus S naught equal to KB ln of 1 equal to 0, because ln of 1 equal to 0. When the initial entropy of the system is selected as 0, the following value of S can be obtained as S minus 0 equal to 0. Because S equal to 0. Thus, the entropy of a perfect crystal at absolute 0 is 0. Thank you.